We're going to look at section 5.7, which is the square roots and Pythagorean theorem. We have a radical expression here. We would read that as the square root of 15. The two parts that we have are the symbol itself, which is called the radical sign, and the number that's underneath it is called the radicand. And sometimes the radical sign is referred to as a square root sign because we have the square roots being done here, but there's also other roots besides the square that can be calculated. So in general, it is called the radical sign. And now it wants us to look at the first 20 perfect squares and their square roots. When we've been doing math before, we've been looking at functions that undo each other. So when we're solving a problem and we need to get rid of addition, we would subtract. If we need to get rid of multiplication, we would divide, so on. And so when we look at square roots and squaring, they're the same thing. They're opposites. And so when we look at these problems, we can think of going back and forth. So first, let's fill in the column that has the square root because we're looking at the 20 perfect square roots. So the square roots would be 1, 2, 3, 4, 5, and just keep counting up to 20. I would try and talk, but I know if I try and describe something, I'm going to screw up my numbers. So just be patient while I write them. Okay, so when we take the number and have its perfect square, it's asking us to take the number that we wrote, the square root, and take it to the second power. So for number 1, we're going to do 1 times 1, which is still 1. And so if we were going backwards, the square root of 1 is 1. So for the second number, let's take 2 to the second power. 2 squared is 4. So again, if you're going to go backwards, the square root of 4 is 2 because 2 times 2 is 4. And so we're just in the top column taking the number that we have, the square root, and multiplying it by itself or taking it to the second power. So 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared is 225, 16 squared is 256, 17 squared is 289, 18 squared is 324, 19 squared gives us 361, and then 20 squared would be 400. And so if we had those numbers and we're looking at the square roots, for example, let's look at 14. We would say the square root of 196 equals 14, because 14 times 14 is 196. And so in this case, our radicand, the number underneath the radical sign, is 196 if we throw in that vocabulary word that we looked at. And so when we look at these, they call them perfect squares because it's a whole number that we get as an answer. 14 times 14 is exactly 196. Now, before we had calculators to do square roots, people had to try and come up with it by hand. And there's numbers that you'll get that you're trying to find what times itself gives you that as an answer, and it's not a whole number. And so, for example, let's say somebody needed to find the square root of 20. Well, the method that I've used before in a college class actually to have to come up with the answer without using a calculator is called the guess and check method. And so what you would do for this case, for example, is that we would say, well, I know that the square root of 16 gives me 4, and the square root of 25 gives me 5, and so the square root of 20 must be between 4 and 5. Let me just type that because it's a lot quicker. And so we would guess and check until we got closer and closer to 20. So for example, one way would be to check, let's use red again. Check, let's say you're going to do 4.5 and take it to the second power. And if we took 4.5 times 4.5, we would get 20.25. So then maybe we would check 4.4. And if we multiplied 4.4 times 4.4, we would get 19.36. So we would know that it has to be somewhere between 4.4 and 4.5, and so then maybe we'll check 4.45. And you just keep playing around with the numbers until you get closer and closer and closer to the 20, and usually they'll ask you to find it up to maybe 3 decimal places or 4 decimal places. And so that's how you would play around with that using that guess and check method. And so benefits, possible benefits is to learning how to do it by hand is you don't always have a calculator. And the idea is, even if you do have a calculator, you can always ask, does my answer make sense? That's one thing that I've mentioned several times, that you might not always know what the right answer is, but you do something that's like, whoa, there's no way that's even possible. And so if maybe you hit something in the calculator wrong or something like that, knowing where you're going with a problem and what the approximate answer could be would help you determine whether your answer makes sense or not. So knowing square roots is important when looking at problems dealing with right triangles. And in this case, we're going to look at the Pythagorean theorem right now. In a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the two legs. And so in this picture, the hypotenuse is C. Your hypotenuse is always the one that's across from your right angle. And they call the legs A and B. And it doesn't matter which one you use first, but it's saying that if I take the length of the two legs and add them together after they're squared, that is going to give me the same number as the square of the length of the third one. And so when you do this, notice you're going to get C squared equals, and then A squared plus B squared. You're going to be given numbers to plug in, and so we would have to, in the formula, if we are going to try and solve it, let's say that we get this number, and that represents C squared, we're going to have to square root it to get C by itself, because again, square root and square are opposites. They undo each other. So the square is getting undone by the square root symbol. So let's take a look at an example that shows us kind of why this formula works. And so here's a visual representation of squaring. We know that squares are side times side, just like squaring a number. And so notice we have a square of length of 4 next to this leg, a square side length of 3 on this leg, and then the hypotenuse has a square that has 25. So it says to find the area of each square. Well, let's put that in our picture after we find the answer. We know that, let's call this A, B, and C. Again, it doesn't matter which one's A and B. C has to be the one across from the right angle, our hypotenuse. So for A, the area of that square would be 4 to the second power, or 4 times 4, which will give us 16. B would equal 3 squared, 3 times 3, which would equal 9. And C would equal 5 squared, or 5 times 5, which is 25. Then it says to write the area of the largest square, which would be your hypotenuse square, which would be C, which we got as 25, as the sum of the other two. So A squared plus B squared, in this case we got 16 plus 9. And we see that 16 plus 9 is 25. So 25 equals 25, because again, this was 5 squared equals 4 squared plus 3 squared. And then we see that 25 does equal 25. So it checks. And so the equation from the Pythagorean theorem, we just did that. So A squared plus B squared equals C squared, or if you write it as C squared equals A squared plus B squared, it doesn't matter. So then we have all of our work already done up there. So there's no point in rewriting it. So the similarity is that we're using the same numbers. Same numbers, same numbers. Okay, so as you can see, that is why the formula works, is because when we look at the square units of each of the legs, it gives us the same amount as the square of the hypotenuse. And so again, if we didn't know what C squared was and we were plugging it in, we would have to find out what that missing length is, and we'll have practice doing that in a minute. A Pythagorean triple is a set of three counting numbers that satisfy the Pythagorean theorem. One example of the Pythagorean triple, 3, 4, 5, was used in the proof that we just did. There are several formulas that can be used to create these triples. And so the next problems explore how to create these Pythagorean triples. The easiest method is to create more triples to start with a known Pythagorean triple, and then you multiply each triple by the same whole number. So for example, since we know that 3, 4, 5 is a Pythagorean triple, we can multiply everything by 2, which would give us 6, 8, 10 for another Pythagorean triple. Now it says use the Pythagorean theorem to verify that this works, this triple. So we need to know that 6 squared plus 8 squared equals 10 squared. So again, that longest length has to be your hypotenuse value, or C. So that's why I knew that 10 was going to be by itself across the equal sign. 6 squared is 36. 8 squared is 64. And 10 squared is 100. And if we add 36 plus 64, we will get 100. So to create two more, well, they doubled it, so let's triple it. And so let's multiply 3 times our 245. Or I'm sorry, our 345. Why did I say 2? Which would give us 9, 12, 15. And then let's multiply it by 4. So let's quadruple our 3, 4, 5 triple. And we'll get a new Pythagorean triple of 12, 16, and 20. And then again, we could verify that if need be to show that 12 squared plus 16 squared equals 20 squared for that one, or for our other one, 9 squared plus 12 squared equals 15 squared. Okay, here we have another way to create a Pythagorean triplet. It says that if we use two numbers, n and m, and it says they are integers, which means are positive and negative numbers, then our a number can be taken by the difference of the squares, n squared minus m squared. B is 2 times their product, so 2 times n, and C would be the sum of their squares, n squared plus m squared. So if they use the example of n equals 2 and m equals 1, that's where we would get our 3, 4, 5. And so they want us to come up with different numbers. And so let's use n equals 6 and m equals 5 and see if we can do this. So our a value, it says we're taking n squared minus m squared. So we have 6 squared minus 5 squared, which would give us 36 minus 25, which gives us 11. Our b value, well, let's use a different color so it's easier to separate it. That is 2 times n, so it's 2 times 6, times m, which is 5. So 2 times 6 times 5 will give us 12 times 5, which is 60. And then our C value, instead of A with the subtraction, it's going to be addition. So we're going to have 6 squared plus 5 squared, which would give us 36 plus 25, or 61. So now we have to use these numbers to make sure that it works. We have to verify it. So again, our formula is a squared plus b squared equals c squared. And so we'll have 11 squared plus 60 squared, and that needs to be the same as taking 61 squared. 11 times 11 is 121. 60 times 60 is 3,600, or 3,600. And then 61 squared is 3,721. And if we add 121 to 3,600, we get 3,721, which matches our C squared. So it did work. Okay. So for practice, for the first part, it's asking you to just use the calculator to find the square roots of these. And so again, in your calculator, you're going to do your square root button, and then 14, and then hit equals. And it says to the nearest thousandth, which is 3 decimal places. Make sure you're careful on how you round, and pause the video to do that. Check your work in the answer key, and when you're ready, then we'll go on to some story problems where we're putting some more applications in with our square roots. So our first one, it says a police officer needs to tape off a crime scene. The crime scene took place in a park that has a fence along one side and a shed near the fence. The shed is 8 feet long and the fence is 17 feet long. The officer wants to attach the caution tape from the edge of the shed to the edge of the fence. And so the length is represented here with an X. How much caution tape does he need? So the first thing is, let's establish which side is our hypotenuse. Here's our right angle, and across from that is our C value. And it doesn't matter which side we label as A, which side we label as B. Let's do our top is A and our 8 is B. So we would need to plug that into our formula. We have A squared, which is our unknown, so X squared, plus B squared, which is 8, equals our C squared, so 17 squared. So when we solve this, we will get X squared plus 8 times 8 is 64, equals 17 times 17 is 289. Now notice our X squared is not by itself where we need it to be able to take the square root. And so what we're going to do is subtract the 264 from both sides. So let me write that up here. X squared plus 64 equals 289. And we subtract 64 from both sides. So we can zero that out. And so our X squared equals 225. So again, to take and get x by itself, we need to take the square root of 225 to undo that square, which gives us 15. And that's in feet. So our missing side was 15 feet long. Part B asks us what's the area of our crime scene area. And so we know the area of a triangle equals 1/2 times base times height. Remember, the base and the height are perpendicular, so that's the length of our legs. And so we'll do 1/2 times, let's do, if we look at the triangle sideways, the base is 8, and the height then would be our 15. And half of 8 is 4, and 4 times 15 would be 60. And this is area, so we have square feet. So the length around would be our 8 feet and our 15 feet for our legs, 17 feet for our hypotenuse, and then the area inside a triangle is 60 square feet. Our other story problem we have for an example says Aya has a triangular wooden porch attached to the side of her house. The legs of the triangular porch measure 12 and 16 feet. She is decorating for a party and has 18 feet of party lights. Does she have enough to put along the entire railing of the longest side of the porch? The longest side is going to be our hypotenuse, and so we need to be able to do our a squared plus b squared equals c squared. So we have 12 and 16 as our legs, and that's our hypotenuse squared, so we'll say it's c squared. 12 times 12 is 144, and 16 times 16 is 256. And so when we add those, we get 400 equals c squared. And so c will equal the square root of 400, which equals 20. Says she has 18 feet, so the answer is no. She does not have enough. She's 2 feet short. If yes, how many feet are left over? If no, how many additional feet? Oh, I already answered that. I jumped the gun. We need 20 feet. We have 18. So we need 2 feet more. Not quite enough. And our last story problem, the maximum walking speed of an animal depends on the length of their legs. To calculate the maximum speed an animal can walk, which is in feet per second, multiply the square root of the animal's leg length by 5.66. So the first one, we have a 6 feet length leg of a giraffe, and so the maximum, it said we're supposed to take that leg length and square root it and multiply that answer by 5.66. And to the nearest hundredth is 2 decimal places, so the square root of 6 times 5.66 gives us approximately 13.86, and that's feet per second. Feet per second. And then the man has 3 feet long legs approximately, so we'll plug in 3 for the length, and we need to multiply that by 5.66. And that gives a man's walking speed of approximately 9.80 when we round it 2 decimal places, feet per second. It says, since the giraffe's legs are twice as long as a man's legs, does it mean a giraffe could walk twice as fast? If not, how did the speeds compare? Well, 9 times 2 is 18, so even ignoring the decimal places, we can see that it's not double. And so we would say no. And if we divide 18 or 13.86 by 9.80 to see what the ratio is, we can say that the giraffe's speed is about 1.4 times faster than the man's speed. So again, we got that by making that a ratio. And many of you have done that kind of thing before, making it that unit rate when you're looking at the IV story problems and stuff like that. So the giraffe is about 1.5, not quite 1.5 times faster than man. Questions while you're working on 5.7 homework? Send me an email. Otherwise, I'll see you in 5.8.